Let's talk about a voltage divider bias or emitter bias with one supply. Now, for my voltage divider, I have a 250 ohm resistor here and a 20K on here. And the emitter, and why we call it emitter bias, is that the emitter has the 250 ohms on the emitter, nothing on the collector up here. So what we want to find is the resistance at the base and the voltage at the base and the current coming out of the base or going into the base. Now, we use Thevenin's theorem. We just short out the power supply. So we take the top of R1, put it to the bottom of R2 down here. That puts these two in parallel. And then we calculate the resistance. So the parallel resistance is just R1 times R2 plus R1, divided by R1 plus R2. And that comes out to 246.9 ohms. Okay. Now, to find the voltage on the base, we take our 5 volts here coming in, and we multiply that by our R2, and then we divide it by R1 plus R2. So here it is here, and that comes out to 4.938 volts. Now we want to find the current at the base here. So the base current is going to be equal to the voltage, which is our VN, our base voltage, minus the drop across our diode here, drop from the base to the emitter, which is going to be about 0.6 volts. And then we divide that by our resistance. The resistance of our voltage divider here, which is 246.9 ohms. And then we add our emitter resistance here times the beta of the transistor times the gain on the transistor. So that's 132 times our, in this particular case, it's 132 times our 250 ohms. And if we calculate that out, it comes out to 127 microamps on the base. Now to find our collector current, we just take our base current and we multiply it by the gain of the transistor. So we multiply that by 132, and it comes out to 16.8 milliamps. Okay, so what's happening up here is that the, we say current flows in this direction down from the collector down to the emitter, but electrons are actually flowing in this direction from the emitter to the collector and from the emitter to the base and out the base. Okay, so the emitter is, in this case, it's N material and it's heavily doped. It's got a lot of electrons in it, and the collector is moderately doped with extra electrons. But the base is a thin layer and it's P material, and it just has holes in it, but it's lightly doped, which just has very few holes in there. It creates two depletion regions on these PN junctions in the base there, and with the electrons facing in and the positive charges are facing the N material. Now, no current's going to flow through there, can't get through the depletion region, but if we make this side of the base more positive, then electrons can flow, through the emitter out through the base here. And for every electron that we get out of the base or take out of the base, 132 of them can flow through the base to the collector. Okay, because our gain is 132. If we had a gain of 200, then 200 electrons would pass through there. So that's why we can take our base current times our gain, in this case 132, and that gives us our collector current there. Now the emitter current is going to be a little bit higher because some electrons are going through there, but only 1 in 132 of them. So that's kind of a very basic way that thing's working, but that's how we can calculate our collector current there. So we'll see if the math actually works. So I set it up right here. I'll put this at milliamps, and this one I'm going to set to microamps, and I'm going to turn the voltage on, and we've got 127.5 microamps, and it says here we had 127.48, pretty good. It's dropping a little bit, and over here we have a 16.86 milliamps. Okay, and this here we had 16.8 over here, so I got a negative here. I got this backwards, but that's fine. And so anyway, it's close, according to these meters anyway. And so we're looking pretty good there. Now, what I'm going to do here, and why I picked these numbers here, is that I'm going to take this on the base here, this 250 ohm resistor, I'm going to replace it with this infrared detector. Now, when the infrared detector doesn't have any light coming into it, any infrared light coming into it, it has a resistance of about a couple megohms. And then as you shine light into it, it'll drop down to 250, maybe get below that to 200 ohms. Okay, so it should be fairly close to the to that 250 ohms there. Now on the emitter over here, I'm going to put an LED in there with I think I've got about 140 ohms on that. So, and what I'm trying to do there is get the same current for the emitter bias here. So it should be around 16 milliamps here. So this is going to replace this 250 ohm resistor here, and this one's going to replace this resistor up here. And then when we shine light in here, or shine infrared light in here, it should turn on the LED down here. Okay. So now you have to reverse bias these here. So you have to put the negative up here and the positive down here. That's how these infrared detectors work. So I'm going to put that together, and we'll see if that works. See if the amperage is the same, and check it out. All right, I've got I replaced the 250 ohm resistor in the emitter with a LED and in series with a resistor, about 140 ohms or so. I wanted to get the same current, and the base resistor, I substituted the infrared detector in there. Now you have to reverse bias those detectors. That's how they work. So this is infrared light here, and we'll shine it on here, and that lights it up. And what do we have here? We've got, I can keep it on there. Yeah. 16.5 milliamps and 125 microamps on the other side. So depending how, if I get it closer, it's 128 microamps and almost 17 there. So not bad. So this is going to work out fine. And so the math is working out good. And that's how you put together a infrared detector. Okay. So thank you.